Hello class, this is Calculations with Heating Curves Part 2. In my previous video, I introduced some vocabulary such as your specific heat capacity, your heat of fusion, and your heat of vaporization. So if you would like to know the differences between those vocabulary terms, please check out my video for Part 1. In this video, we'll be talking about the equations that are associated with those vocabulary terms and how they show up on our heating curve. So let's go ahead and get started. Recap a little bit. Your specific heat capacity was when we raised 1 gram of a substance 1 degree Celsius. That means we're changing its temperature. On my heating curve, there are certain regions where my temperature is changing, and it's anytime you have a vertical increase. When we're flatlining here, we don't have a change in temperature. That whole process is occurring at this temperature. It's not changing throughout that process. So, because I'm changing my temperature, I'm speeding up my particles, I've got more thermal energy at this phase in my heating curve, I need to account for my heat to include a temperature change. Now, quick recap of what heat is. Heat we use as an abbreviation Q, so this means Q, or heat means Q. And earlier this year we saw a comparison between a bucket of 50 degrees temperature water and a little tiny teacup of 100 degrees temperature water. And through that discussion we found that heat is related to both the amount of particles that you have and the temperature that they carry with them. So with your heat, we've got our amount of particles, our temperature that they're going through, and because each substance is going to have a different specific heat capacity, we include that in our equation, where this is the mass, this is the specific heat capacity, and this is our temperature change. Minor detail about temperature change. Your temperature change is your final temperature, whatever you're ending at, minus your initial temperature. That is how we calculate temperature changes in chemistry. It's not necessarily the big number minus the small number. You have to keep in mind whether you're heating up or cooling down, because that changes what your temperature change would be, either positive or negative. Now, because we have this temperature change component, and our specific heat capacity is based on increasing 1 gram, 1 degree Celsius, then on our heating curve, we're going to use this equation wherever we have a temperature change. So that would include this location right here. Q is equal to mc delta T. And because we are solid during this phase, we're going to use the value of C for a solid. Again, each individual substance has a different number for C because they absorb different amounts of heat in order to raise their temperatures. For your solid, C for solid is going to be 2.1 joules per gram degree Celsius. So if you're within this region, either warming or cooling, anywhere between 0 as ice and negative numbers, you're going to use the equation Q is equal to mc delta T because we have a temperature change. Now, the minute we start heating up some more, I'll kind of separate this. Let me keep going with this equation. Again, anywhere we have temperature changes. So we have a temperature change when we've got this line, then we flatline, then we have a temperature change here, starting at 0 degrees, going up to 100 degrees. This is all an increase in energy, it's all an increase in temperature as well. So we're going to keep that same equation here, Q is equal to mc delta T, except the difference is that now we're a liquid phase. So our C value would be for liquid. Well, C for liquid, and if we're looking at liquid water, it's going to be 4.18 joules per gram degree Celsius. It takes a lot more energy to heat up liquid water than it does to heat up solid water. About twice as much, 4.1 versus 2.1. The other location that we have an increase in temperature is if we're increasing our gas. So we can use this equation, Q is equal to mc delta T. Again, it shows up wherever you have a temperature change. And instead of these numbers, we would use the specific heat for a gas, which, if you're curious, it actually ends up being about 2.0 joules per gram degree Celsius, slightly a little less than your solid. Now, that is because we have temperature changes. There are some spots on your curve where you're not changing your temperature. You're flatlining instead of increasing temperature. Well, that's because instead of changing the speed of your particles, we are now changing their arrangement. You can speed up particles, you can pull them apart, but you can't do both at the same time. So by changing the arrangement of our particles from going solid to liquid, we need to pull them apart. We need to break down our solid's lattice work and turn it into a liquid. Well, one of my vocabulary terms that talked about breaking apart that lattice work, pulling your solid apart so it could become a gas or could become a liquid, that melting process, it's your heat of fusion. So our equation here is that our heat is based on how many particles we have that we're pulling apart. So that's based on my mass, and I need to include my heat of fusion for that substance. So when I'm flatlining in this region of your graph, I'm using the equation Q is equal to mHF. Now, for water, HF is a constant. It has its own number. HF is 334. And our unit we talked about earlier is joules per gram. Now, another region where we're not changing temperature is going to be up here when we're boiling or evaporating. Again, we aren't speeding up our particles. We are instead taking them in their liquid phase, heating them up, giving them enough energy to pop out of that liquid phase, to spread out, to take up some more space. So that they're no longer right next to each other and moving around right next to each other and sliding past each other. We need to have a big distance between them. So the amount of energy it takes to do this process, pulling those moving around particles further apart to become a gas, is our heat of vaporization, the amount of heat needed for liquid particles to spread out and become gases. It's based on how many particles we have. If we have a lot of particles, it takes more heat. And then we're going to include our HV constant, where this is the heat for your vaporization. For water, this value is 2,260 joules per gram. It takes a lot more heat to pull your particles from your liquid than it does to pull your particles from a solid. Okay, so those are the equations and the constants and how they show up in our heating curve based on whether we're changing our temperature, so using the Q is equal to mc delta T, or whether we're changing our phase and pulling our particles apart. So our HF for when we're melting or freezing, and our HV for when we are condensing or evaporating. Hope that was helpful. Tune into part 3 where I actually start using these equations to calculate values.